Hey guys, my name is Dr. Rothschild. I grew up in New Greenwich, Connecticut. I've always had a passion for software and fell deeper in love after attending Yale, where I graduated with a degree in computer science and quantum physics. Today we are going to embark on Python and everything you will need to become an expert in this programming language. Python sits at the heart of programming and is perhaps the easiest language to learn. This week marks the beginning of an adventure into the remarkable world of Python programming. Python, as you will soon discover, is not just a programming language. It is a versatile tool that can empower you to create, automate, and innovate in a multitude of fields. Why Python? Now, some of you might be wondering why we chose Python as the language for this course. Python stands out for its elegance, simplicity, and readability. It serves as an ideal starting point for beginners because it enables you to quickly grasp fundamental programming concepts without getting bogged down by complex syntax. A brief history. Before we delve into the practical aspects of Python, let's take a moment to appreciate its rich history. Guido van Rossum, Python's creator, initiated its development in the late 1980s. Python's naming inspiration, the British comedy group Monty Python, hints at the language's whimsical nature. Since its inception, Python has evolved into a powerful and influential language. Python's universal appeal. One of Python's most compelling attributes is its universal appeal. It's not confined to a single niche, it's everywhere. Google's search engine, Instagram's photo sharing platform, NASA's space missions, and Dropbox's cloud storage, all powered by Python. Its versatility knows no bounds. Getting started, setting the stage. Before we immerse ourselves in Python's world, we need to set the stage. This begins with installing Python on our machines. Rest assured, the installation process is straightforward, and I will guide you through it step by step. Your first Python code. Once we have Python installed, we will embark on an exciting journey to write our very first Python program. We will use Python's Integrated Development and Learning Environment, IDLE, for this purpose. Brace yourselves to witness the magic of making the computer respond to your commands. Understanding the basics. Our journey commences with the fundamentals. Python provides us with a toolkit that includes variables, data types, and simple arithmetic operations. These are the building blocks that we will use to construct our programs. The power of variables are the heart of programming. They enable us to store and manipulate data. In Python, you can create variables to hold integers, floating point numbers, or even text. We'll soon explore these concepts hands-on, crafting your first Python program. But theory only takes us so far. We learn best by doing. Together, we will craft a simple Python program that calculates the area of a rectangle. This exercise will introduce you to the core concepts of Python programming, including variables and mathematical operations. Preview of next week. As we conclude this inaugural week, I encourage you to look ahead with anticipation. In week 2, we will dive deeper into Python syntax. We will explore how to make decisions using conditional statements and how to repeat tasks with loops. Your homework assignment. Before we part ways for this week, I have a homework assignment for you. First and foremost, ensure that you have successfully installed Python and written your first Python program. Beyond that, I encourage you to explore Python further on your own. Try different commands, experiment, and let your curiosity be your guide. Now, I open the floor to questions, whether they pertain to Python, the course, or any other topic. Please feel free to ask. We are here to support one another on this exhilarating journey. In closing, I want to express my excitement about the weeks to come. Python has a unique way of blending simplicity with limitless potential. Together, we will unlock that potential and become proficient Python programmers. Thank you for joining this adventure. I look forward to seeing you next week, ready to explore Python's syntax and the captivating world of control structures. Thank you and have a wonderful week. Hello guys, I hope everyone enjoyed their weekend. Before I jump into this lecture, I want to have a really deep conversation. I was at church on Sunday, and the sermon touched on Matthew 7. The scripture focused on not passing judgment. This was a very interesting message, and I took a lot from it. How does this tie into Python, you might ask? I believe in our society today, we often overlook what is considered technology. While I was listening to the church service, I came to the realization at one point in time the book was the pinnacle of technology. Human technology and civilization ultimately progressed in our ability to store data. The first notable advancement was human language. This allowed us to auditorily transmit data to one another. Populations that had human language were able to progress at unprecedented rates. In comparison to populations who did not, What followed soon after was the advancement of written language. This brought with it a way of more efficiently educating populations. As written language became more advanced, the book arose as perhaps the most monumental data storage tool. Its application allowed for the formation of complex religions and stories. Our concept of Jesus is often heavily misunderstood because it is important to realize many people during this time were illiterate, and the concept of a book would have been viewed how we would look at flying cars today. Also, in the same way that many people today cannot understand programming languages, so user interfaces were created for a more iterative experience for users. This holds true for religious text. Many people could not read, so a pastor or priest was absolutely necessary. In the Bible, it is noted that Jesus was a perfect person. This was because characters written in books were real to the imagination of readers. In week 1, we laid the foundations of Python's Wonderland. In week 2, we venture further into the labyrinth of control structures. Much like Theseus navigating the intricate maze, we too shall navigate the labyrinthine nature of Python programming, the control structures paradigm. Consider Python as a vast and intricate control structures paradigm, where control statements serve as the compass, leading us through the convoluted paths of decision-making and repetition, not unlike the enigmatic twists and turns of a conspiracy theory. Deciphering decision-making enigma. Within the realm of Python, we are confronted with the enigma of decision-making. The if, elif, and else statements akin to cryptic clues allow us to direct the flow of our code, orchestrating actions based on conditions as though we were deciphering a cryptic conspiracy. Crafting code as an art form, Python's if statements are akin to the crescendos in a symphony, creating moments of dynamic execution, much like a punchline in comedy. They imbue your code with an artistic touch, allowing it to respond differently to varying conditions, resembling a well-timed comedic punchline. Mastering loops, a journey through time loops in Python reminiscent of temporal loops in narratives like Groundhog Day transport us through time. Much like Bill Murray's Recurring Day, loops enable us to execute code repeatedly until specific conditions are met, invoking a sense of déjà vu. The for loop, temporal mastery. The for loop serves as a temporal vessel, facilitating the repetition of code a predetermined number of times, akin to the DeLorean in Back to the Future that propels us into the past or future of our program's logic. The while loop. Code's inception. Conversely, the while loop conjures the sensation of inception, where code manifests in layers of logic, persistently executing until a certain condition is no longer true, plunging deeper into the essence of your program's design. Code reusability. A sacred practice. In the realm of programming, code reusability assumes a sacrosanct nature, resembling religious doctrine. Functions in Python encapsulate the wisdom of code, much like religious texts containing timeless teachings. These functions ensure the sanctity of your code structure. Exploration in Week 2. In Week 2, we shall immerse ourselves in the profound world of Python's control structures. We will master the art of if statements, embark on a journey through for and while loops, and delve into the sacred practice of code encapsulation through functions. Through this, you shall attain mastery over the orchestration of your code's destiny. In conclusion, Python's control structures serve as the sculptor's tools, allowing you to craft the reality of your code. As artisans of Python, you possess the power to shape and mold your programs into exquisite masterpieces. Thank you for joining us in Week 2 of our Python voyage. Brace yourselves for a captivating week ahead as we unlock the true potential of Python's control structures. Python is an object-oriented programming language. Unlike some other object-oriented languages, however, Python doesn't force you to use the object-oriented paradigm exclusively. It also supports procedural programming with modules and functions so that you can select the best paradigm for each part of your program. The object-oriented paradigm helps you group state, data, and behavior code together in handy packets of functionality. Moreover, it offers some useful specialized mechanisms covered in this chapter, like inheritance and special methods. The simpler procedural approach based on modules and functions may be more suitable when you don't need the pluses one of object-oriented programming. With Python, you can mix and match paradigms. In addition to core OU concepts, this chapter covers abstract base classes, decorators, and metaclasses. Classes and instances. If you're familiar with object-oriented programming in other OU languages such as C++ or Java, you probably have a good grasp of classes and instances. A class is a user-defined type, which you instantiate to build instances, that is, objects of that type. Python supports this through its class and instance objects. Python classes. A class is a Python object with the following characteristics. You can call a class object just like you'd call a function. The call, known as instantiation, returns an object known as an instance of the class. The class is also known as the instance's type. A class has arbitrarily named attributes that you can bind and reference. The values of class attributes can be descriptors, including functions, covered in descriptors, or ordinary data objects. Class attributes bound to functions are also known as methods of the class. A method can have any one of many Python-defined names with 2 leading and 2 trailing underscores, known as dunder names, short for double underscore names. The name underscore underscore init underscore underscore, for example, is pronounced dunder init. Python implicitly calls such special methods when a class supplies them, when various kinds of operations occur on that class or its instances. A class can inherit from one or more classes, meaning it delegates to other class objects the lookup of some attributes, including regular and dunder methods that are not in the class itself. An instance of a class is a Python object with arbitrarily named attributes that you can bind and reference. Every instance object delegates attribute lookup to its class for any attribute not found in the instance itself. The class, in turn, may delegate the lookup to classes from which it inherits, if any. In Python, classes are objects' values, handled just like other objects. You can pass a class as an argument in a call to a function, and a function can return a class as the result of a call. You can bind a class to a variable, an item in a container, or an attribute of an object. Classes can also be keys into a dictionary. Since classes are perfectly ordinary objects in Python, we often say that classes are first-class objects. The class statement. The class statement is the most usual way you create a class object. Class is a single-clause compound statement with the following syntax. Class name is an identifier, a variable that the class statement, when finished, binds or rebinds to the just created class object. Python naming conventions advise using title case for class names such as item, privileged user, multi-use facility, etc. Base classes is a comma-delimited series of expressions whose values are class objects. Various programming languages use different names for these class objects. You can call them the bases, superclasses, or parents of the class. You can say the class created inherits from, derives from, extends, or subclasses its base classes. In this book, we generally use extend. This class is a direct subclass or descendant of its base classes. **KW can include a named argument metaclass equals sign to establish the class's metaclass, too, as covered in how Python determines a class's metaclass. Syntactically, including base classes is optional. To indicate that you are creating a class without bases, just omit base classes, and optionally also omit the parentheses around it, placing the colon right after the class name. Every class inherits from object, whether you specify explicit bases or not. The subclass relationship between classes is transitive. If C1 extends C2 and C2 extends C3, then C1 extends C3. The built-in function is subclass C1 C2 accepts 2 class objects. It returns true when C1 extends C2, and otherwise it returns false. Any class is a subclass of itself. Therefore, is subclass CC returns true for any class C. We cover how base classes affect a class's functionality in inheritance. Class private variables. When a statement in a class body or in a method in the body uses an identifier starting but not ending with 2 underscores, such as underscore underscore ident, Python implicitly changes the identifier to underscore classname underscore underscore ident, where classname is the name of the class. This implicit change lets a class use private names for attributes, methods, global variables, and other purposes, reducing the risk of accidentally duplicating names used elsewhere, particularly in subclasses. By convention, identifiers starting with a single underscore are private to the scope that binds them, whether that scope is or isn't a class. The Python compiler does not enforce this privacy convention. It is up to programmers to respect it. Class documentation strings. If the first statement in the class body is a string literal, the compiler binds that string as the documentation string or docstring for the class. The docstring for the class is available in the underscore underscore doc underscore underscore attribute. If the first statement in the class body is not a string literal, its value is none. See docstrings for more information on documentation strings. Descriptors. A descriptor is an object whose class supplies one one or more special methods named underscore, underscore, get underscore, 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 set underscore, underscore, or underscore, underscore, delete underscore, underscore. Descriptors that are class attributes control the semantics of accessing and setting attributes on instances of that class. Roughly speaking, when you access an instance attribute, Python gets the attribute's value by calling underscore, underscore, get underscore, underscore on the corresponding descriptor, if any. For example, overriding and non-overriding descriptors. When a descriptor's class supplies a special method named underscore, underscore, set underscore, underscore, the descriptor is known as an overriding descriptor, or using the older confusing terminology, a data descriptor. When the descriptor's class supplies underscore, underscore, get underscore, underscore, and not underscore, underscore, set underscore, underscore, the descriptor is known as a non-overriding descriptor. For example, the class of function objects supplies underscore, underscore, get underscore, underscore, but not underscore, underscore, set underscore, underscore. Therefore, function objects are non-overriding descriptors. Roughly speaking, when you assign a value to an instance attribute with a corresponding descriptor that is overriding, Python sets the attribute value by calling underscore, underscore, set underscore, underscore on the descriptor. For more details, see attributes of instance objects. The third dunder method of the descriptor protocol is underscore, underscore, delete underscore, underscore, called when the del statement is used on the descriptor instance. If del is not supported, it is still a good idea to implement underscore, underscore, delete underscore, underscore, raising a proper attribute error exception. Otherwise, the caller will get a mysterious attribute error. Underscore, underscore, delete underscore, underscore exception. The online docs include many more examples of descriptors and their related methods. Instances. To create an instance of a class, call the class object as if it were a function. Each call returns a new instance whose type is that class. An underscore instance equals sign C5. The built-in function is an instance I, C, with a class as argument C, returns true when I is an instance of class C or any subclass of C. Otherwise, is instance returns false. If C is a tuple of types 3, 10 plus or multiple types joined using the vertical bar operator, is instance returns true if I is an instance or subclass instance of any of the given types, and false otherwise. Underscore, underscore, init, underscore, underscore, when a class defines or inherits a method named underscore, underscore, init, underscore, underscore, calling the class object executes. Underscore, underscore, init, underscore, underscore on the new instance to perform per instance initialization. Arguments passed in the call must correspond to with init des parameters except for the parameter self. For example, consider the following class definition. Class C6, def, init self, n, self.x equals sign n. Here's how you can create an instance of the C6 class. Another underscore instance equals sign C6, 42. As shown in the C6 class definition, the underscore, underscore, init, underscore, underscore method typically contains statements that bind instance attributes. An underscore, underscore, init, underscore, underscore method must not return a value other than none. If it does, Python raises a type error exception. The main purpose of underscore, underscore, init, underscore, underscore is to bind and thus create the attributes of a newly created instance. You may also bind, rebind, or unbind instance attributes outside underscore, underscore, init, underscore, underscore. However, your code is more readable when you initially bind all class instance attributes in the underscore, underscore, init, underscore, underscore method. When underscore, underscore, init, underscore, underscore is absent and not inherited from any base class, you must call the class without arguments, and the new instance has no instance-specific attributes, attributes of instance objects. Once you have created an instance, you can access its attributes, data, and methods using the .us operator. For example, attribute references such as these have fairly rich semantics in Python. We cover them in detail in Attribute Reference Basics. Annotating your Python code with type information is an optional step which can be very helpful during development and maintenance of a large project or a library. Static type checkers and lint tools help identify and locate data type mismatches in function arguments and return values. IDEs can use these type annotations, also called type hints, to improve autocompletion and to provide pop-up documentation. Third-party packages and frameworks can use type annotations to tailor runtime behavior or to auto-generate code based on type annotations for methods and variables. Type annotations and checking in Python continue to evolve and touch on many complicated issues. This chapter covers some of the most common use cases for type annotations. You can find more comprehensive material in the resources listed at the end of the chapter. Python is fundamentally a dynamically typed language. This lets you rapidly develop code by naming and using variables without having to declare them. Dynamic typing allows for flexible coding idioms, generic containers, and polynomial polymorphic data handling without requiring explicit definition of interface types or class hierarchies. The downside is that the language offers no help during development in flagging variables of incompatible types being passed to or returned from functions, in place of the development time compile step that some languages utilize to detect and report data type issues. Python relies on developers to maintain comprehensive unit tests, especially though far from exclusively one, to uncover data type errors by recreating the runtime environment in a series of test cases. Type annotations are not enforced. Type annotations are not enforced at runtime. Python does not perform any type validation or data conversion based on them. The executable Python code is still responsible for using variables and function arguments properly. However, type annotations must be syntactically correct. A late imported or dynamically imported module containing an invalid type annotation raises a syntax error exception in your running Python program, just like any invalid Python statement. Historically, the absence of any kind of type checking was often seen as a shortcoming of Python, with some programmers citing this as a reason for choosing other programming languages. However, the community wanted Python to maintain its runtime type freedom, so the logical approach was to add support for static type checks performed at development time by lint-like tools, described further in the following section, and IDEs. Some attempts were made at type checking based on parsing function signatures or docstrings. Guido van Rossum cited several cases on the Python developers mailing list showing that type annotations could be helpful. For example, when maintaining large legacy codebases. With an annotation syntax, development tools could perform static type checks to highlight variable and function usages that conflict with the intended types. The first official version of type annotations used specially formatted comments to indicate variable types and return codes as defined in PEP 484, a provisional PEP for Python 3, 5.2. Using comments allowed for rapid implementation of and experimentation with the new typing syntax without having to modify the Python compiler itself. 3. The third-party package MyP gained broad acceptance, performing static type checking using these comments. With the adoption of PEP 526 and Python 3.6, type annotations were fully incorporated into the Python language itself, with a supporting typing module added to the standard library. Type checking utilities. As type annotations have become an established part of Python, type checking utilities and IDE plugins have also become part of the Python ecosystem. MyPy. The standalone MyPy utility continues to be a mainstay for static type checking, always up to date, give or take a Python version, with evolving Python type annotation forms. MyPy is also available as a plugin for editors including Vim, Emacs, and Sublime Text, and for the Atom, PyCharm, and VS Code IDEs. PyCharm, VS Code, and Wing IDE also incorporate their own type checking features separate from MyPy. The most common command for running MyPy is simply mypy mypython script.py. You can find more detailed usage examples and command line options in the MyPy online documentation, as well as a cheat sheet that serves as a handy reference. Code examples later in this section will include example MyPy error messages to illustrate the kinds of Python errors that can be caught using type checking. Other type checkers. Other type checkers to consider using include MonkeyType. Instagram's MonkeyType uses the set profile hook to detect types dynamically at runtime, like PyType, see below. It can also generate a PyI stub file instead of, or in addition to, inserting type annotations in the Python code file itself. Pydantic. Python uses exceptions to indicate errors and anomalies. When Python detects an error, it raises an exception. That is, Python signals the occurrence of an anomalous condition by passing an exception object to the exception propagation mechanism. Your code can explicitly raise an exception by executing a raise statement. Handling an exception means catching the exception object from the propagation mechanism and taking actions as needed to deal with the anomalous situation. If a program does not handle an exception, the program terminates with an error message and traceback message. However, a program can handle exceptions and keep running despite errors or other anomalies by using the try statement with except clauses. Python also uses exceptions to indicate some situations that are not errors and not even abnormal. For example, as covered in iterators, calling the next built-in function on an iterator raises stop iteration when the iterator has no more items. This is not an error. It is not even an anomaly, since most iterators run out of items eventually. The optimal strategies for checking and handling errors and other special situations in Python are therefore different from those in other languages. We cover them in error checking strategies. This chapter shows how to use exceptions for errors and special situations. It also covers the logging module of the standard library in logging errors and the assert statement in the assert statement. The try statement. The try statement is Python's core exception handling mechanism. It's a compound statement with three kinds of optional clauses. It may have 0 or more except clauses, defining how to handle particular classes of exceptions. If it has except clauses, then it may also have right afterwards one else clause, executed only if the try suite raised no exceptions. Whether or not it has except clauses, it may have a single finally clause, unconditionally executed, with the behavior covered in try/except/finally. Python's syntax requires the presence of at least one except clause or a finally clause, both of which might also be present in the same statement. Else is only valid following one or more excepts. Try, except. Here's the syntax for the try, except form of the try statement. This form of the try statement has one or more except clauses, as well as an optional else clause and an optional finally clause whose meaning does not depend on whether except and else clauses are present. We cover this in the following section. The body of each except clause is known as an exception handler. The code executes when the expression in the except clause matches an exception object propagating from the try clause. Expression is a class or tuple of classes, in parentheses, and matches any instance of one of those classes or their subclasses. The optional target is an identifier that names a variable that Python binds to the exception object just before the exception handler executes. A handler can also obtain the current exception object by calling the exe_info function 3. 11 plus or the exception function of the module sys. When an exception is raised, execution of the try suite immediately ceases. If a try statement has several except clauses, the exception propagation mechanism checks the except clauses in order. The first except clause, whose expression matches the exception object, executes as the handler, and the exception propagation mechanism checks no further except clauses after that. Specific before general, place handlers for specific cases before handlers for more general cases. When you place a general case first, the more specific except clauses that follow never execute. The last except clause need not specify an expression. An except clause without any expression handles any exception that reaches it during propagation. Such unconditional handling is rare, but it does occur often in wrapper functions that must perform some extra task before re-raising an exception. See the raise statement. Avoid a bare except that doesn't re-raise. Beware of using a bare except and except clause without an expression unless you're re-raising the exception in it. Such sloppy style can make bugs very hard to find, since the bare except is overly broad and can easily mask coding errors and other kinds of bugs by allowing execution to continue after an unanticipated exception. New programmers who are just trying to get things to work may even write code like, exception propagation terminates when it finds a handler whose expression matches the exception object. When a try statement is nested lexically in the source code or dynamically within function calls in the try clause of another try statement, a handler established by the inner try. A typical Python program is made up of several source files. Each source file is a module, grouping code and data for reuse. Modules are normally independent of each other so that other programs can reuse the specific modules they need. Sometimes, to manage complexity, developers group together related modules into a package, a hierarchical, tree-like structure of related modules and subpackages. A module explicitly establishes dependencies upon other modules by using import or from statements. In some programming languages, global variables provide a hidden conduit for coupling between modules. In Python, global variables are not global to all modules, but rather are attributes of a single module object. Thus, Python modules always communicate in explicit and maintainable ways, clarifying the couplings between them by making them explicit. Python also supports extension modules, modules coded in other languages such as C, C++, Java, C#, or Rust. For the Python code importing a module, it does not matter whether the module is pure Python or an extension. You can always start by coding a module in Python. Should you need more speed later, you can refactor and recode some parts of your module in lower level languages without changing the client code that uses the module. Chapter 25, available online, shows how to write extensions in C and Python. This chapter discusses module creation and loading. It also covers grouping modules into packages, using setup tools to install packages, and how to prepare packages for distribution. This latter subject is more thoroughly covered in Chapter 24, also available online. We close this chapter with a discussion of how best to manage your Python environment SDS. Module objects. In Python, a module is an object with arbitrarily named attributes that you can bind and reference. Modules in Python are handled like other objects. Thus, you can pass a module as an argument in a call to a function. Similarly, a function can return a module as the result of a call. A module, just like any other object, can be bound to a variable, an item in a container, or an attribute of an object. Modules can be keys or values in a dictionary and can be members of a set. For example, the sys.modules dictionary discussed in module loading holds module objects as its values. The fact that modules can be treated like other values in Python is often expressed by saying that modules are first-class objects. The import statement, the Python code for a module named anami, usually lives in a file named anami.py as covered in searching the file system for a module. You can use any Python source file 1 as a module by executing an import statement in another Python source file. Import has the following syntax: import modname as varname. After the import keyword come one or more module specifiers separated by commas. In the simplest, most common case, a module specifier is just modname, an identifier, a variable that Python binds to the module object when the import statement finishes. In this case, Python looks for the module of the same name to satisfy the import request. For example, this statement, import myModule, looks for the module named myModule and binds the variable named myModule in the current scope to the module object. Modname can also be a sequence of identifiers separated by dots to name a module contained in a package, as covered in packages. When as varname is part of a module specifier, Python looks for a module named modname and binds the module object to the variable varname. For example, this, import myModule, as alias looks for the module named myModule and binds the module object to the variable alias in the current scope. Varname must always be a simple identifier. The module body. The body of a module is the sequence of statements in the module's source file. There is no special syntax required to indicate that a source file is a module. As mentioned previously, you can use any valid Python source file as a module. A module's body executes immediately the first time a given run of a program imports it. When the body starts executing, the module object has already been created, with an entry in sysmodules already bound to the module object. The module's global namespace is gradually populated as the module's body executes. Attributes of module objects. An import statement creates a new namespace containing all the attributes of the module. To access an attribute in this namespace, use the name or alias of the module as a prefix. Import myModule a =, myModule def, or import myModule as alias a =, alias. This reduces the time it takes to import the module and ensures that only those applications that use that module incur the overhead of creating it.